Charlie, 10,000.
Unfortunately, we are not here to teach you how to gamble. We do not condone gambling in any way, but it's a really, really useful way to talk about probability, or kind of the likelihood that something is going to happen. Now, to start us off, there are a few key words that we need to look for. And as we go through the lesson of some very, very basic ideas of probability, these are some big things to watch out for. So obviously this idea of probability, frequency, how to calculate that, what a binomial process is, and the way to take kind of the English language and, or, and not, and turn that into a way to calculate very basic ideas of probability. So let's start at the very beginning, is good old probability, and that is the likelihood that something will occur. It doesn't mean that it is going to occur, but we are trying to figure out the likelihood that it's going to happen. So unless something's 100%, obviously it may or may not happen. Now, for probability, there's four big components that we want to take into account when it's kind of setting the boundaries of the systems of the calculation. And the first is the experiments. And this is the activity, the thing that you are designing so that you can get results from. So are you flipping a coin? Are you rolling some dice? Are you, do you have a deck of cards? Those are all experiments. And the sample space is the set of all possible outcomes. So if I am rolling a die, I can get a 1, a 2, a 3, a 4, a 5, a 6. Those are all possible outcomes when I roll that thing once. The event is what I want to focus on. Do I want to see how many times I roll a 1? Do I want to see the probability of drawing an ace? What is that subsection of the sample space that I want to look at? And then at the end, what is the outcome? What is the result? So as an example, let's say we go with the most basic thing. You're just tossing a coin, and we're asking, probability-wise, what's the probability of a flipped coin landing heads up? So the experiment that we are defining is obviously flipping the coin. That is the thing that we are doing to get observable results. The second thing is the sample space. What are all the possible outcomes that can happen when we flip a coin? Assuming that it's not going to land on its side for whatever reason, because I think I would argue based on our experiment, even that is extremely, extremely low. The outcomes are it's going to go heads or it's going to go tails. But the one thing that we are focused on, the event that we are trying to calculate, is landing heads up. So we're focused on a portion of the probability tree, and so we're going to flip the coin. We're going to see what happens, and that will help us kind of figure out our probability. So that's kind of our broad scope of how we look at probability itself. Now again, this doesn't mean that something is going to occur. It is the likelihood of how often might that happen, and we're always going to express that as a number between 0 and 1. So it's usually a fraction or maybe a decimal as far as what we're dealing with. Now we can convert that to a percentage really easily, because a lot of times we like to say, oh, there's a 50% chance that this is going to happen, is a little bit more common than saying 0.5, our fraction for that. But keep in mind that every probability of every possible result, if we add those up, should equal 100%, or 1 if we're talking about it in essentially decimal form. Now let's talk about how to actually calculate this, and we're going with what we call relative frequency. So how often is this thing actually going to happen? So more often than not, we're looking for what that frequency is. We're going to use the symbol F to represent that. And to calculate that, we are going to look at our target outcome. So how many times can we get a specific outcome divided by the total number of events? And again, we are expressing that number either as a fraction or a decimal, and if we need to, we can convert that to a percent. So let's do an example of this. Again, going back to flipping our coin, usually the easiest thing. Let's say we want it to land heads up. That is our sample space. So if I look at a coin, either it's going to be heads up or tails up. So I have one desirable outcome, which is heads up. And for a coin, I have two possible outcomes. So I have one desired, I have two possible. So when I'm calculating the frequency of that probability happening, I just take my desirable divided by my possible, and that will give me my overall probability. So it's 1 over 2, 0.5 if we want to convert that to 50%. But hopefully you guys already knew that playing around with flipping coins. Now, on the flip side, we can do the same thing with landing tails up. So if we look at that, we have one desired outcome, which is tails, out of 2 possible. So again, it's 50%. So all those possibilities add up to 100%, which means we are good to go. Now, we get into a little bit dicier territory when we're talking about multiple throws. So let's kind of talk about what that might look like. Let's say we're looking for the probability of tossing a coin up twice and having it land heads up both times. So if we kind of use a probability tree, and let's say we have our first flip and we could get either heads or tails. The second flip, we have a few more combinations. So we have, if we go heads the first time, we could get either heads or tails. If we get tails the first time, we can go either heads or tails. So really, the only route we can go to get heads both times is 1 out of those 4. So we have one desired outcome where we get heads both times. From our tree, we see that there are 4 possible outcomes, which means if we want to get heads both times, we have a probability of 0.25 or 25%. So again, we just need to focus on what do we want the outcome to be and how many possible outcomes are there. Now let's do another one. If we toss the coin 3 times and have it land heads up exactly twice. So if we do our probability tree, we do heads or tails. We do our second one. Each of those could be either heads or tails. Now we have a third flip, and all of those could be either heads or tails, and we can kind of tally all of those up. So we are specifically looking for landing heads up exactly 2 times. So using that tree, we can figure out our desired outcome divided by the total number of outcomes. So if we look at the tree and kind of analyze those, it looks like 3 possibilities of landing heads up exactly 2 times out of a possible 8 throws. So again, if we calculate that out, we have about 37.5%. Not too shabby. Now, this is what we call a binomial process, where 2 things happen. There's only 2 possible outcomes, and the trial outcomes are independent, which means tossing a coin doesn't mess with future flips. So I can flip that coin 1,000 times, and none of those flips are interrelated. Just because I flipped a heads the first time doesn't mean I'm going to get the heads second time. All of those trials are completely independent. So if we take it back to the video at the beginning of these notes, we can go back to roulette. So the idea of roulette is you spin the table, you toss a little ball in there, and the ball is going to go into one of these pockets that correspond to a certain number. So casinos are using this idea of probability to adapt to how much money you can potentially win, which means the lower the probability, the more money you could win. Again, we are not condoning gambling, but a casino is full of really cool ways to think about how we use probability all the time. So if we think about a roulette wheel, you have 38 total pockets, including the 0 and the double 0. You have 18 that are red, you have 18 that are black, and then you have the 0 and the double 0. Now, towards the bottom, if you look at the roulette table where you can essentially place your bets, there's a lot of different ways that you can put that forward. You can bet on red. So you can say, all right, I'll put my money on if it's red or not. I can put my money on if it's black or not. So depending on how unlikely it is, you can get more money. So there's a lot of different ways to pick. You could pick one number. You could pick the 12, like the first 12. You can pick second 12, third 12. You can pick a column, or I guess a row if we look at it like this. Or obviously you can pick a 0 or double 0. So there's a lot of different ways to try to win some money based on what you might potentially roll. So the first piece of probability we're going to use in conjunction with frequency is and probability. So we're trying to figure out the likelihood of this and that happening simultaneously. So how we're going to do that is we need to figure out what the frequency of one outcome is, the frequency of the second outcome, and we're going to do a little fancy math with that to figure out how probable it is to get both of those. So if they are independent, like we are working with for right now, then the probability of two separate things happening, all you have to do is multiply those frequencies together. So let's do an example of that. We need to figure out the frequency of certain things, and then we're going to use that to figure out the overall probability. So let's say we are rolling some dice. And if you look at a standard D6 die, you have 6 different things you can roll. So the first question we want to ask ourselves is, what is the probability, or what is the frequency of rolling a 4 on a single die? And if we look back on our coin example, the number of desirable outcomes is 1, because we are looking to see if we get a 4. That is our sample. And our possible outcomes, there are 6 possible outcomes. So we have 1 desired, 6 possible, which means the frequency of rolling a 4 on a single die is 1 over 6, or roughly 0.17, like 17%-ish, or 16.666666666. Now let's do the same thing for a 1. So if I roll that die, there's 1 desired outcome, which is a 1, and there are 6 possible. So the probability, or the frequency of rolling any number on that die, is going to be 1 out of 6. Easy peasy. So now the question is, what is the probability of rolling a 4 and then a 1 in back-to-back rolls? And that is where we use that multiplication piece, where we know the frequency of rolling a 4 is 1/6. We know the frequency of rolling a 1 is 1/6. Because we're trying to see if both of those will happen in succession, we need to multiply those together, which means we have a 1 out of 36 chance, or roughly 2.78%. So not very good. Probably not a good idea to take that to the bank. Now we can use the same idea for or if we want a 4 or a 1 to happen. So instead of using and in multiplication, we can use or, which means we add those probabilities together. So in the same way where we multiplied the probabilities or the frequencies of a 4 and a 1, we can add those to see if we can get or. So again, to either roll a 4 or a 1, that's going to increase our frequency quite a bit. So if we go through that same process, we still know based on our die, it's a 1 in 6 chance to get a 4. It's a 1 in 6 chance to get a 1. But if we're asking ourselves the probability of rolling a 4 or a 1, all of a sudden, if we add those up, 1/6 plus 1/6, or 2/6, you have a 33% chance of getting a 4 or a 6. And obviously you can use the same way of saying 2 out of 6, because 2 desired outcomes out of 6 possible outcomes, but this is kind of a simple way to do that. So notice how going from roughly 3% now to 33% is a big jump when we talk about having 2 things happen in succession versus having options or for addition. Now the last one that we're going to talk about is not probability, and that is where the event is not going to occur. And we're splitting hairs just a little tiny bit, but all we can do is if we figure out the likelihood that something will happen, we just have to take 1 minus that probability. So again, I know we're splitting hairs a little bit, but sometimes it's a little bit more useful to figure out if something is not going to happen versus if it will. So let's do the same thing. Obviously, we can do this in our head, but what is the probability of not rolling a 1 on the die? Now, you can look at it and you can say, okay, there are 5 desired outcomes out of 6 possible outcomes, but we're going to use kind of this not probability to help us solve for that. So we're going to take 1 minus the frequency of rolling a 1. And we know that the desired outcome is 1 out of the possible outcomes is 6. So if we take 1 minus 1/6, we have 5/6 or 83.33%. Again, when you get to more complicated situations, maybe this is useful, but if we're talking about just one die, probably not worth it to take 1 minus. We can essentially just take the desired divided by our total amount. So those were binomial processes, essentially. But there are other processes that change depending on what you do. So if trial outcomes are dependent on what happened before, we have to think a little bit harder about the desired outcomes and the possible outcomes. So for example, if you draw a card and you discard that card, all of a sudden the probability of drawing another card depends on what you drew before, because our deck is smaller and we kind of lose out on one of those cards. So let's talk about just the very, very basic probability of those cards, assuming that we have 52 cards in a deck. And our overall goal, the overall thing that we want to solve for, is the probability that the first card that we get is an ace, and the second card is either a face card or a 10. Now there's some information that we need to know about this deck before we can really figure that out, in case you're not super familiar with them. So we need to know how many cards are in a deck. And if we talk about a standard deck, it's going to be 52 cards. If we talk about how many aces there are, there's going to be 4. So you have a diamond, a heart, a spade, and a club. And then face cards, what we mean by face cards are like kings, queens, and jacks. And since there are 4 suits, there's 12 total face cards, and there's going to be 4 total 10. So we're going to take this basic amount of information, and we're going to do some probability with that. So again, remember that there are 4 suits, or essentially those shapes: hearts, diamonds, spades, and clubs, which means that there are 4 of kind of each number or each face card within the deck itself. So let's go through the process real quick and figure out the individual frequencies before we figure out our overall problem. So the probability that the first card is an ace. Now if we think about a deck of cards and we draw that first card, we know that there are 4 aces in the deck, and at this point we know there are 52 cards in the deck. So if we take our desired outcome, which is 4, or aces, divided by 52, which is the total amount of cards that we have in the deck, we find, by dividing those, we get a decimal number of 0.07, roughly 7, which means we have a 7.7% chance of drawing an ace on the very first card that we draw. I guess not too shabby. Now the hard part comes in, is now that we've drawn that ace, that changes the probability of our next card. So we know that the first card was not a face card because we said we drew an ace. We need to figure out what is the probability that the second card is a face card, so a jack, a king, or a queen. Now based on the last slide we talked about, there are 12 face cards in a standard deck, but for our overall outcome, since we just took 1 card away from the deck, there are now 51 cards in the deck. So that changes the frequency of drawing a face card after drawing an ace. So the way we're going to calculate that is 12 is the number of desired outcomes, which is a face card. So there's 12 cards in that deck. But now there are only 51 cards total in the deck because I drew that ace and I took that away, I discarded it, whatever. So by finding that frequency, we know that we have a 23.53% chance of drawing a face card as the second card within that deck of 51. The third thing we need to figure out is the 10. So we can take that same idea. So that first card we know is an ace. The overall goal is we're trying to figure out what are the odds of drawing an ace and either a face card or a 10. So let's say we go back to drawing that first card. We draw an ace. The second card, there are 4 10s in the deck, so my desired outcome is 4. And because I already drew that ace, I know there's 51 cards in the deck now, which means I have a 7.84% chance of getting a 10. Notice how my probability went up because I have less possible outcomes to choose from. So now we have the frequencies of drawing an ace right off the bat. I have the probability of drawing a face card as my second card, and I have the probability of drawing a 10 as my second card. So we need to put all of those together. Again, first card is an ace, and the second card is either a face card or a 10. So let's take that language and let's kind of turn it into an equation. So my idea is this overall probability is I need to find an ace as my first card, and so because of that keyword, I'm going to multiply the second card being a face card or a 10. So notice the or statement, I am using addition to show that my second card can either be a face card or a 10, which increases my odds. But I also want an ace to be drawn out first. So notice how we have the or statement right here, a face card or a 10. My first card has to be an ace and either a face or a 10. So we already know the frequencies of each of those. We can just plug it into the equation. So we know that 1 over 13 is the odds of drawing, or excuse me, the probability of drawing an ace, and we know that the odds of drawing a face card and a 10. So all we have to do is do a little bit of fancy-pantsy math, and we find that the probability of drawing an ace and then a face card or a 10 is about 2.41%.